In this video, we will learn two main theorems. First one is Archimedean property for the set of real numbers, and second one is the set of all rational number is dense in R. So, the statement for first one is if x, y element of R, x, y both are set of real numbers and x is more than 0, okay, then there is a positive integer n such that nx is more than y. So, this is the statement of Archimedean property of the set of real number. It says that on the real line, so this is infinity, this is positive infinity, this is 0, okay, this is real line. So, x, y is a real number, but x should be more than 0, okay. So, you can guess x anywhere in this interval. So, x would be in this interval, okay, and y can be anywhere. Y can be either this interval or that interval, okay. So, suppose x is here, this is x and this is y, okay. Now, we need to prove that there is a positive integer n such that nx is more than y. So, proof, we will prove this one by contradiction. Suppose, okay, we can write proof by contradiction. So, proof by contradiction. That means, suppose there is no real number, there is no positive integer n such that nx is more than y, okay. We are assuming that there is no positive integer n such that this one is true, okay. That is, so if this is not true, then this should be true. That means nx is less than y. So, if nx is less than y, then what is n? N can be written as y over x, okay. So, n is less than y over x. So, what does this means? This means that is y over x would be the upper bound for positive integers, okay. So, this would be upper bound for the positive integer, but we know that this is a contradiction. This is a contradiction. Why? Because because the set of positive integers in so it's going on. So the set of all positive integer has no upper bound. We know this one. It's going on and on. So the set of positive integer is not bounded above. So this cannot be true. That means this is not true, and that means this is true. Okay. So this method is called proof by contradiction. Okay. So we are done for this one. Now using this property we will prove another theorem that's very important. So next theorem, it is the set of all rational number Q is dense in the set of all real number. What does this means? The set of all rational number is dense in the set of all real number. It means that for any two real numbers, between any two real numbers, there is a rational number. It is always true. So if we write between any two real numbers, there is a rational number. Okay. Even we can state this theorem in another way. So, or it can be stated in another way. If x, y element of the set of all real numbers and x is less than y, then there exists a rational number p element of the set of all rational number such that x is less than p is less than y. That means if x and y are two real numbers where x is less than y, then between these two real number there exists a rational number. Always, this is always true. So in number line, if you pick two real numbers x and y, then there exists a rational number between them. This is always true. It doesn't matter how close those two numbers are. So we will prove this theorem. Proof since we have x less than y, we have y minus x more than 0. Okay, since x less than y, so y minus x would be more than 0. Let x equals to capital X equals to y minus x and y equals to 1. Okay. Why we assume that? Because to prove this theorem, we will apply the Archimedean property of the set of all real numbers. Okay, we will apply this theorem to prove this one. So to apply this one, what we need x more than 0, and here our x is more than 0. X is y minus x. This is more than 0. So this x is more than 0. So by Archimedean property, there is a positive integer n such that n capital X more than y. Okay, this was our Archimedean property. Here y can pick from anywhere on the real number line. I pick here y equals to 1. This is a particular number, y equals to 1, because we can pick y from anywhere on the number line. So if nx is more than y, then n, what is x? X is y minus x more than 1. So this one we can rewrite as ny more than nx plus 1. Okay, we can write this one as ny more than nx plus 1. Suppose this is equation number 1. So this is equation number 1. This is a number. Okay, this one is a number. So what we want to do, we want to search an integer m, find a positive integer m such that this ny is between them. That means m less than ny less than m plus 1. So ny is a number. So ny should be between the integer m, okay, m and m plus 1. So if this is m, this is m plus 1. So ny should be anywhere between these two, or even it can be here. That's why I use equal sign. Okay, so ny should be anywhere between them. So from this line, if we consider only this part, if we consider ny less or equals to m plus 1, then we can write ny minus 1 less or equals to m. So ny minus 1 less or equals to m. Okay, and now if you consider this part, so what is this part? That part is m less than ny. Okay, so this is m, so m less than ny. Now from this line, from equation 1, ny is more than nx plus 1. So what is ny minus 1? So in equation number 1 we have ny more than nx plus 1. So ny, we have ny minus 1. So ny minus 1 should be more than nx. Okay. So ny minus 1 is more than nx. So we can write this one, nx less than ny minus 1 less or equals to m less than ny. Now if we omit this part, then we can rewrite this one, nx less than m less than ny. Now divide this inequality by n, divide the whole inequality by n. Then what we get? X less than m by n less than y. Let p equals to m by n. This is a rational number, okay, because m is integer, n is also integer. So this is a rational number. So if we assume p equals to m over n, then x less than p less than y. That means between any two real number there exists always a rational number. Okay, that's it. Thanks for watching.